Let's kick off. Hello, everybody. My name is Anil Kokaram from Trinity College Dublin, and I'm here with the other co-industry liaison chair, Hassan Al-Mahiri from Ministry of Education in UAE. And we'd like to welcome you to this industry workshop organized here at ICIP. And we are delighted to welcome the team from Facebook. My job and Hassan's job really is to be invisible during this session because it's going to be run by the Facebook experts who have organized quite a really powerful engineering panel to talk to you about image and video processing in Facebook. So let me now hand over to the chair of the Facebook session, Shankar Raghunathan. Shankar?
Thanks so much, Anil. Hello, everyone. Welcome to the Facebook Industry Workshop. We are doing this for the second year. Last year, we did the workshop in person at ICIP Taipei. And this year, we are being happy to do it virtually. Thank you, everyone, for taking the time to attend this workshop. Let me quickly walk through the agenda of this workshop. First, I'm going to be talking about why Facebook videos are important and some of the unique challenges that we face.
Could you all please mute while the speaker is speaking? Thanks.
And first, I'm going to be talking about why Facebook videos are important and some of the unique challenges that we face for video infrastructure in Facebook. Next, we are going to have a talk on how Instagram optimizes video at scale. The second talk will be on how we can use video quality metrics to optimize video delivery. And the third talk is going to be on how hardware acceleration can be used for energy efficient video transcoding. And that is not all. After this, we are going to have a panel discussion with leading industry experts. And finally, we are going to be taking your question and answers after the panel discussion. And before I go further, let me introduce myself. I am Shankar Raghunathan. I've been working in Facebook for 5 years in the video infrastructure team, working on many of the problems that we are discussing here on video quality metrics, video compression, and how we can do compression in an energy efficient manner. First, why is Facebook videos important? Facebook is the world's largest social network, more than 2.7 billion users. And Facebook videos span multiple products. The Facebook app itself, Instagram, Messenger, and WhatsApp, as well as Facebook video powering other products such as Oculus, Portal, and Workplace. Some of the key Facebook products, recent products, include allowing people to watch live sports in Latin America, such as UEFA Champions League. Next, we have premium music videos where people can watch premium videos for free on Facebook. Next, we have the recently introduced Instagram Reels, which allows people to watch exciting short-form content in Instagram. And then we have Rooms, which allows people to do video chat with their friends and colleagues, as well as broadcast these chats to a broader audience. This allows people to do interviews on panel discussion virtually. While Facebook videos was always important, the importance of Facebook videos has grown even more during this pandemic because it allows people to be connected to their world and to their family and their community. Okay, so now let me talk about what are some of the key problems that we face in Facebook. First, like always, one of the key challenges is to increase the compression efficiency of our videos. That means that we need to reduce the bits at the same visual quality or increase the quality at the same bitrate. At the same time, we need to do this in an energy efficient manner. That is, we need to reduce the compute so that we can reduce both the cost as well as the energy needed to power our data centers. Third, we need to do this while reducing the storage needed for all these videos as the number of videos keeps increasing over time. And we need to do this while also achieving very high levels of stability, reliability, and near infinite scaling. Scale is one of the key important factors that distinguishes Facebook videos, and that dictates many of our choices that we make in our infrastructure. Before I go further, I just want to mention that please keep your questions coming in the chat group, as well as if you want to continue the discussions offline, please send a message at the virtual chat page. We'll have a link posted near the end as well. We also have some swag, and please feel free to grab one. Let me now introduce the next speaker, Haishia, who's going to be talking about how Instagram optimizes video quality at scale.
Hi, thank you, Shankar. Thanks all for attending our workshop. My name is Haishia Shi. I have been working at Facebook for over 2.5 years at the Instagram Media Infra team. And today I'm going to give a brief talk on how we try to optimize our video quality at scale for Instagram. Next slide, please. Yes. So first of all, we are looking at the problem of improving video quality from end to end. On the player side, the way that we improve playback experience is through ABR, or adaptive bitrate streaming. And that means that player needs to have a set of encodings that are readily available to select for the optimal version based on bandwidth. And player needs to continuously stream and possibly dynamically switching between those different quality streams based on real-time bitrate estimate. And what that means is that a certain amount of processing is required on a server for this to be available. Server needs to generate multiple encodes for the same input video. And it needs to make some decisions to select different resolution, bitrate, and quality settings up front. And all of these encodes needs to form a set with aligned keyframes to allow seamless transition between different quality. Next slide, please. So this itself is not really a difficult thing, but the challenge it comes with the scale. We have a very huge upload volume in excess of many millions of daily uploads. Transcoding all of these videos are computationally expensive because, first of all, the number is high, and for each one of those videos, we need to do many different transcoding jobs. Efficiency in terms of compute and energy is really the most important requirement here. Even though Facebook has a lot of data centers and we have a very large compute capacity, there's still not enough when you average this by the huge number of uploads. It's not enough to achieve the best compression efficiency for all. And finally, IG is a product where users tend to share their low quality mobile camera captures that have compression artifacts to begin with. So it's quite different from the professional made content and the applicable technique for them. Next slide, please. So our goal of optimization is pretty much aligned with the whole Facebook organization in improving compression efficiency, in reducing the computation cost, and to ensure high reliability. However, all these three goals tend to work against each other. So we need to find the best compromise that will get the best of all of them. Next slide, please. So I'm going to briefly talk first about the selection of the optimal encoding set. This is actually a pretty difficult problem. And to simplify this, we simply treat this problem as a 2D search space for encoding parameters. Typically, you have a target quality mode where you need to select the resolution and the quality parameter, or a CRF, or sometimes you do the target bitrate, you select resolution and bitrate. But in either case, you have a 2D search space. And on the right, you basically exhaustively try all the possible combinations, and you measure the quality for each of those encoding, and you get this result. So if we plot all of them together, you get this bitrate and SSIM, or it could also be PSNR or some other quality metric. and you put it on a scatter plot. Next slide, please. Ideally, what we are looking for is the so-called convex hull. It's this selected red subset of dots that represents the optimal encoding set for any given bit rate. This is representing the best quality that you can possibly get within this 2D search space. The problem, however, is that it's too computationally expensive to try all the combinations and then select a subset. Obviously, we really cannot afford to try like dozens or hundreds of encodings for every upload. What we really need is a low-cost heuristic to approximate this convex hull. Next slide, please. So at Instagram, what we basically do is a very cheap heuristic. We start with the intuition that we can very easily assess the blurriness of the input. For example, in this example, the leftmost input is very sharp, and on the right-hand side, it's very blurry, and in the middle, it's somewhere in between. Next slide, please. So what do we do with all these three categories of contents? For very blurry content, what we get is it has very low downscaling distortion. In other words, when you do the encoding selection, it actually favors downscaling first. Lowering the QP while lowering resolution means that it works better for smooth images, and you are not really losing too much due to downscaling. So that will be on the left here, where we basically try to reduce the resolution first, and then when we reach some kind of a minimum threshold, we start to increase the CRF. On the other hand, if it's a very sharp content, then you don't want to downscale very easily. You want to increase the QP. Even though that introduces some compression artifacts, it is usually hidden by the high complex images. So that is the solution in the middle. And finally, for everything in between, what we do is try to find a transition point, and then it will be the middle of the two. Next slide, please. So this is like one heuristic we try to bypass the cost of finding the convex hull. On a global level, however, we also face the question of prioritization. We do not have enough computation power to apply the full encoding set for all the uploads. So there's the question of which ones we prioritize. And these are the three principles. First, by content popularity. We can either do a static prediction based on the known characteristics of the creator, or by real-time monitoring for viral content. But we tend to prioritize content that gets watched more. And secondly, for the product characteristics, if some content has a long shelf life and it has a longer attention span, then it will get higher priority than things like direct message or short stories that tends to expire in a very short time. And finally, we take into consideration the different cost of a video codec. For example, VP9 is more computationally expensive than H.264, so we cannot really apply the same priority for these jobs. We take into account that VP9 is X times slower than H.264, so it will require a higher amount of engagement to compensate. So that is a short summary of some of the tactics we use to optimize encodings at scale. Next, I'm going to hand over to my colleague Cosmin, who's going to talk about how we optimize video delivery using the visual quality metrics. Thank you.
Hi, my name is Cosmin, and I've been at Facebook for a little over a year and a half, and I work on the media algorithms team focusing on optimizing video quality at scale. And today I'm going to talk to you about optimizing video delivery using visual quality metrics. Next slide, please. So why would we want to limit playback options and not play the maximum possible quality, particularly on cellular networks, if we want to optimize quality? Well, there's several different reasons. One very common reason is to conserve data on metered connections. While some users may have effectively unlimited cellular data, most users are on limited data budgets, and we have to make sure that we maximize their enjoyment of that data on a, say, per gigabyte basis. That's a reason to do something like this on a year-round basis. In addition to that, we also have unusual situations where we have to react to, for example, submarine fiber cuts or other emergencies that lead to temporary either surge in demand or a loss in capacity. And an example of that was earlier this year during the early days of the COVID crisis, when suddenly large amounts of users were suddenly spending a lot more time online and watching a lot of online video, which was putting a large strain on the ability of networks to handle it, and perhaps leading to a loss of ability to use the network for something more important, such as video conferencing, suddenly working remotely, etc. So that was a time where we needed to react and essentially limit the qualities that we play in order to reduce demand on the network and protect the network for more critical uses. Also, for our own reasons, we may want to protect the non-video traffic in an emergency for Facebook itself, so that people can use the application to be able to communicate with their friends and family, and maybe watch a little bit less video or spend a little bit less data on the video that they watch, so that we can protect that traffic. And then lastly, in some situations, we may want to improve the quality of experience beyond the limit of the client-side adaptive bitrate algorithm, where we notice in certain situations we may want to nudge it towards a particular end of the spectrum in order to maximize that utility. And this is something that may change over time as the client-side algorithms become smarter and more able to rapidly deal with changing network conditions. Next slide, please. So now that we established why we may want to limit the qualities we play, let's look at some options for how we can decide where to put those limits. A very common way to do this is to do it based on, say, resolution. So we may want to limit playback to no higher than 720p or 480p, 360p, etc. It's a very common way to look at it. Another way to look at it is to do it based on bitrate. So we can say draw a line at 1 megabit or 500 kilobits, etc., and pick the limits that way. But really, the way I want to talk to you about today that we found works very well in practice is to do it based on the quality of the video. And this is something that ends up driving more optimal ways of doing it. Next slide, please. So in theory, we can change between bitrate and quality somewhat interchangeably. For a given video at a specific point, for a given amount of bits, we can find the quality, and we can express the same limit as a quality limit or a bitrate limit, and it doesn't really matter. This is in theory. In practice, we'll see on the next slide. There's a wide variety of videos, and at the exact same bitrate, the quality may vary somewhat widely. So here's an example of 2 different videos and a few different points, and we can see that at the same bitrate, the blue video above and the orange video below have wildly different qualities. And we can imagine the graph goes from lowest possible quality to highest possible quality. We see the blue is looking quite good, while the orange video is on the quite poor end of the spectrum at the exact same bitrate. Next slide, please. So here's an example at 400 kilobits using a VP9 encode across a wide variety of videos. We can see the variation in quality score on a scale of 0 to 100. And this is due to the wide variety of content and viewing conditions, which leads to a large variance in quality at the same bitrate in practice. And this is the situation that we want to avoid. Next slide, please. So if we think of the quality on a scale of 0 to 100, there's some 3 distinct areas within that scale that I think are important to keep in mind. There's a range where the quality itself is not annoying. The user can watch the video and the quality kind of gets out of the way and they don't really notice it and they can just enjoy the content. There's a part of the spectrum where the quality is a little bit annoying, but it's acceptable. The user can continue to watch, they'll notice the occasional slight impairments, but it's not so bad that they would stop watching. And the last is the not acceptable end of the spectrum, where the quality is so bad that the user would either stop watching and maybe go do something else. So we want to avoid situations where we nudge the user in the unacceptable range of the spectrum, and we want to keep it, at worst in the annoying but acceptable range. And that's why it's important to keep the quality within a tighter bound rather than allowing it to vary all over the scale. Next slide, please. So here's how we can define those quality limits in practice. We can define some threshold at the max. So we can say this is the maximum quality, and anything above this quality we will not play. And this can be in the not acceptable or the not annoying acceptable end of the spectrum. We can also then define a minimum quality threshold where the unacceptable range starts. So we can say we want to definitely make sure that we play something above unacceptable. And then we can use some upper and lower bound bitrate safeguards to ensure that we don't go either way too high in the quest to avoid low quality, and we don't go way too low in the quest to avoid too high of a quality. And this is primarily necessary because the underlying metrics that we use themselves are not 100% reliable, and they may have situations where for certain content, they may be unusually low or they may be unusually high. So in order to avoid situations where we cannot trust the metric itself, we define some bitrate safeguards to avoid this and keep the quality of experience somewhat reasonable even in those extreme conditions. And we can set different limits for intentional viewing and for autoplay as an example. So if we know that the user is really engaging with this content, we may choose to use higher limits. And if we think the intention to watch the video is somewhat more marginal, then we can use perhaps lower limits as an example. Next slide, please. So here's the example with the same videos before using these 4 limits that I mentioned earlier, and I'll explain the lines in a second. So we can look at the yellow line being the higher upper quality threshold, the green line being the low quality threshold, and then the blue line on the left being the low bitrate safeguard, and the red line on the right being the high bitrate safeguard. So we want to make sure that we place something below the yellow, ideally, but above the green. And above the green is critical, such that if there's nothing below yellow, we still want to make sure we're above green, even if we have to violate the upper constraint, as we see in both of these cases. And we want to place something to the right of the blue line and to the left of the red line. So in practice, for these specific videos, this ends up being these 2 points. And we see that whereas before there was a wide variation between the 2 contents, now they're a little bit closer quality-wise. The blue is playing a little bit lower, and the orange video, which is more difficult, is getting a higher bitrate allowance and getting a slightly better quality. Those 2 are now closer together, and therefore there's a much tighter spread on the variation in quality. Next slide, please. So in review, some of the benefits of using MOS or quality-based limits instead of bitrate or resolution limits is that we can result in a more consistent user experience. It will reduce the incidence of unacceptable quality and can deliver in practice equivalent data savings to the other methods while having much better user experience. And it's particularly good as a year-round way of optimizing usage on metered network connections and ensuring that users get consistent quality for less bits. Next slide, please. So we looked today at a few different options. We talked briefly about resolution, bitrate, but really quality as being the primary way of doing this. And next, we're going to consider looking at slope, perhaps. We can use slope to perhaps determine points of diminishing returns of quality per additional bits. So that's something we're going to look into over the coming year. And who knows, maybe next year we'll talk more about that. Next slide. Thank you so much. Again, I'm Cosmas Tajirian, and next, I'll hand it over to my colleague Visala to talk about hardware acceleration for energy-efficient video transcoding. Thank you.
Hello everyone, thank you Cosmin. I am Visala from Facebook Intra-ASIC team. I joined Facebook 2 years ago. My work here focuses on the hardware solutions for video transcoders and other video pipelines. Today, I'll be giving an introduction to hardware acceleration by energy-efficient transcoding. Our agenda also includes cross-codec and HDR encoding, quality metrics, architecture, and results and conclusion. In Facebook, billions of videos get processed here both at Facebook and Instagram every day. Each uploaded video is typically viewed on various devices under different resolutions and bandwidths. The input user upload video may or may not be at its best quality. So it becomes very critical that any processing done by Facebook servers does not lower the input quality of the videos. How is this done? Let us now look at the typical video transcoding flow at Facebook. The client uploads videos. A decoder that supports multiple codec standards then decodes the video. The decoded video is now the FP original, is then scaled to multiple resolutions by a scaler. The scaler is very generic and can perform upscaling or downscaling operations. The scaled videos are then encoded by an encoder. the encoder is tuned for very high quality. They are also encoded at multiple bit rates. The current software encoder supports H.264, VP9, and AV1 standards. Then the quality scores are measured at the input to understand the quality of the uploaded video. Then for each encoded bit stream as compared with its original, which is called the playback quality score, and the quality score for the encoded bit stream independent of the original, which is called the overall quality score of the video. All this is then used by the ABR, which is adaptive bitrate streaming, to dynamically decide on which video is sent to the user based on the user's environment. In this flow, the encoder, which has a very deep pipeline, and the quality measurements, which are pixel-based, consume a lot of CPU cycles, and hence a lot of power. By using hardware acceleration for the decoder, scaler, encoder, and quality measurements, we can save about 30 megawatts of continuous power. Encoder optimizations are chosen such that the compute is reduced while we preserve quality across multiple codecs and to efficiently process the HDR input. With this, I now hand it over to Gaurang to talk about the cross-codec and HDR encoding.
Thank you, Visala. Hi, everyone. My name is Gaurang Chaudhary. I have been at Facebook a little over 2 years, and my work is centered around video encoding optimizations, algorithm complexity optimization, and mapping algorithms on hardware. At Facebook, we employ multiple codecs like H.264, VP9, and AV1 in the video pipeline, and it becomes important to always look for optimizations in the system. These are the few possible video encoding optimizations that we want to discuss today. Cross-codec optimizations help to reduce encoding computational requirements of supporting multiple codecs. 10-bit encoding optimizations, that is using lower precision data path for compute-intensive blocks like motion estimation and mode decision. Both of these techniques helps in software encoding and also in the hardware ecosystem. Next slide, please. We presented the paper on cross-codec data sharing in SPIE Applications of Digital Image Processing 2020. Cross-codec idea is to share the decisions of most compute-intensive blocks, motion estimation, and mode decision data from one codec into another, thereby saving the computational requirements of the system. This can be effective when a new codec is an evolution of older codec, such as VP9 to AV1, where more tools are added to realize bitrate savings for the same quality. Cross-codec data sharing can be done completely in software, or if someone is planning for specialized hardware for few codecs, a hybrid software-hardware solution can be utilized where hardware-generated data can be hooked up to a software encoder for the newer codec. Many VOD systems employ a convex hull approach to decide the best rate control settings for encoding. This is another avenue where cross-codec data can be shared. It can also help with ASIC implementations for multiple codecs. Next slide, please. So, what type of data can be selected for cross-codec data sharing? The qualified data to be shared should satisfy at least one, if not all, of the following. It should be compute intensive. It needs to conform directly or through a mapping with the standard normative requirement of the target codec. The coding inefficiency is acceptable after reusing this cross-codec data. The overhead it generates to the target codec can be absorbed seamlessly. Next slide, please. These are some of the results with cross-codec optimizations of sharing VP9 data for AV1 encoding. We present results for the Facebook internal dataset, which are 400 top viewed public videos from the Facebook pages and has video contents across different resolutions. These show coding efficiency results using VD rate with respect to three popular video metrics, video quality metrics, the SSIM, PSNR, and VMAF. All comparisons are made with Anchor as libvpx 1.8.0 at CPU speed 1 preset. The vertical axis is the BD rate delta percentage, where the negative values indicate it is better than the Anchor, and the horizontal axis is the different versions of VP9 AV1 encodings. The first column set shows that our internal VP9 experimental codebase is close to libvpx 1.8.0. The second column set shows BD rate reduction of libOM 2.0.0 at preset CPU speed 1. As expected, AV1 has significant gains 30 to 35% compared to VP9. The third column set shows the quality of VP9 AV1 equivalent encoder, that is the AV1 toolset equivalent to the VP9 toolset. It is interesting to note that even without computationally expensive features, we can get good gains 10 to 16%, which comes from the better design of intra-inter modes, adaptive entropy coding, inter-referencing structures, and post-processing filters. The last column shows the results for AV1 VP9 share quality, which is where we are using the cross-codec data, that is the VP9 motion estimation and mode decision data for the AV1 encoding. Overall, we still get a gain of 5 to 10% compared to VP9 libVPX 1.8.0 at CPU speed 1 with very little additional computations. Next slide, please. This slide shows the results for the widely accepted JWeight and DERF datasets, and we see similar results for the cross-codec data sharing. The results on DERF dataset are similar to what we see in FB internal dataset. For JWeight, we see slightly better results from the previous slide. Content-wise, both these datasets have good coverage of different types of videos based on complexity. Next slide, please. We can extend the encoding optimizations to 10-bit encoding. Our solution is to replace the compute and power-intensive blocks in high bit depth encoding, like the motion estimation, the mode decision, etc., with the lower precision, that is the 8-bit versions. We tried this experiment in VP9 to demonstrate the concept of using 8-bit versions for 10-bit encoding. Advantage of doing this is primarily the power savings, and secondly, the agnostic architecture for hardware implementation. That means lesser design and verification cycles due to the same blocks getting used in higher bit encoding. Next slide, please. In this slide, we want to highlight some of the key things we used in our experiment. The CRF QP values, the two different video quality metrics used for the BD rate evaluation are SSIM and PSNR, and all comparisons and experiments are made with respect to VP9 internal experimental code base at CPU speed 1 and at constant quality rate control mode for VP9. Next slide, please. In this slide, we show the results of our experiment. The vertical axis is the BD rate delta percentage, where the positive values indicate it is worse than the anchor, and the horizontal axis is the different datasets used in our experiments. The blue columns shows the BD rate delta with SSIM as the quality metric, and the orange columns shows the BD rate delta with PSNR as the metric. As we see here, by replacing the compute intensive blocks in 10-bit with lower precision 8-bit versions, the loss in quality is around 2 to 6% across different datasets. Next slide, please. In this slide, the vertical axis represents the BD rate delta with SSIM as the metric, that is the blue columns from the previous slide, along with the percentage encoding times on the horizontal axis. We observe that while the trade-off in quality is around 2 to 6%, the encoding time is significantly better, around 22% better across multiple datasets. If compared to libVPX CPU speed 2, which is around similar encoding time, the quality is still roughly 2% better. One thing to highlight is even if the quality is on par, the hardware reductions are something that are irreplaceable and overall provide power savings over using lower speed preset for libVPX with full 10-bit encoding. If we consider convex hull approach, using lower precision data path for 10-bit encoding can give us significant computation and power savings. I would now like to hand over to Deepa for discussion on quality metrics. Thank you.
Thank you, Gaurang. Hi all, I'm Deepa Palamadai Sundar from Facebook Infra ASIC team. I joined Facebook about a year and a half ago, and my work focuses on hardware acceleration of video quality metrics. Now that we've seen the hardware improvements for the encoding operation, let's take a look at why a similar strategy would work best for quality metrics as well. Quality metrics is often very complex and it's computed for a wide range of viewport resolutions. Most of these metrics require a per pixel computation, computing components like the local mean and variance, using very elaborate or wide filters like the Gaussian and Sobel filter, using operations like the logarithm operation, also the requirement for very high precision using floating point arithmetic. All these make quality metrics extremely compute intensive, which can consume most of the available resources if it's done in the software pipeline. Here, we show an example of FFmpeg execution times for different viewport resolutions. We are comparing the time taken to do the encode, decode, and QM operation. Here we use the VMAF score compute for the quality metric. We can see that the quality metric takes more time than the encode and decode operation put together. And as the resolution increases, the computational complexity increases and the time as well increases exponentially. So hardware acceleration would offer a more energy efficient solution in this case to compute these quality metrics. Next slide, please. Here we propose a high-level architecture to compute these quality metrics in hardware. Quality metrics in general are classified as full reference, reduced reference, and no reference metrics based on the availability of a reference image to compute the scores. The proposed architecture can support both full reference and no reference metric algorithms. The two main components of this architecture are the DMA controller and the compute kernel. The DMA block is used to fetch the input frames from the memory, and the compute kernel is the one that actually computes the various quality metric scores. Next slide, please. Here are some of the most commonly used full reference metrics supported by the hardware. The first one is the PSNR, or the peak signal to noise ratio, which computes the pixel-wide difference in luminance and chrominance components. The second is the structural similarity index. Here we support two versions of the algorithm. One is the libvmaf version, which is same as the original paper. And the second is the FFmpeg version, which is an approximation using the OLAP 8x8 window algorithm. Next slide, please. The third is the multi-scale SSIM, or the MSSIM metric. This is computed for 5 scales and it uses operation like the Gaussian filtering. The fourth is the VIF, or the visual information fidelity. VIF scores are part of the VMAF metric, and this is computed for 4 scales. Along with the full reference metric, the no reference blurriness metric score is also supported by the proposed hardware. Next slide, please. The compute kernel is the heart of the accelerator. To help with computing metrics simultaneously, we use 3 independent kernels, namely the FFmpeg, the SSIM, and the blur kernel to calculate the SSIM, VIF, PSNR, and the no reference blur scores. This helps us not only to speed the compute, but also saves bandwidth and thereby power. As these metrics are also required to be computed for a wide variety of viewport resolutions, we will need some scaling support to upscale or downscale the input frames to the required viewport size. The proposed architecture also offers inline scalers to do the scaling operation. This will further optimize the bandwidth as it avoids the need to read and write the scaled outputs to and from memory. Additionally, we can also compute block level scores within the frame, and this is extremely useful in identifying regions that have higher impact on quality scores during the encoding process. Now, I hand it over to my colleague Cindy to go over some experimental results and conclude this talk. Thank you.
Hello, this is Cindy. Thank you, Deepa. Hi, my name is Cindy Chen, and my work over the years at NVIDIA, Intel, and now Facebook has been focused on a hardware-friendly algorithm for image processing, computer vision, and computer graphics. The first experiment I will describe compares the read bandwidth used in between a software implementation on the CPU and the proposed hardware architecture. We look at the case where we need to compute the following 3 metrics: SSIM, PSNR, which needs both the reference and distorted frames, and the blurriness metric, which only needs the reference frame. As you can see in the table, in a CPU-based software solution, the same input frame will have to be read again to compute a different metric, so a total of 3 reads for the reference frame and 2 reads for the distorted frame are needed. In our proposed architecture, input images only need to be read once, and the 3 metrics can be computed in parallel. This greatly reduces the bandwidth needed and therefore is more energy efficient. The larger the resolution, the more energy efficiency we will achieve. Overall, we estimate that using the proposed architecture could improve the performance per watt by 100 times comparing to CPU-based solutions. Next slide, please. Our next experiment focuses on algorithm modifications that are needed for hardware implementation. The original CPU-based software algorithm cannot be implemented as is in hardware due to a few challenges. For example, full 32-bit floating point arithmetics on CPU is very expensive for ASIC. Complex mathematical nonlinear functions requires hardware-friendly implementations due to limited area precision and timing. We also need to minimize the number of divisions and applications as they require more hardware complexity and thus more power. Let's take the most complex metric we propose to accelerate, the VIF metric, as an example. The diagram on the right shows the software implementation flow. The original image and the distorted image come in. Let's call them image A and B. First, 3 additional derived images have to be computed. AABB and AB, where AABB are squared of the original images, and AB is the pixel-wise product of A and B. These images are then filtered by a Gaussian kernel, which is how we get the local mean and variances. The VIF score for that scale is then computed using a bunch of multiplication, division, and logarithm operations. These 5 filtered images are then decimated by 2, and similar process will repeat, so we get the VIF score for the next scale. So to do this in hardware, we propose to use fixed point representations everywhere floating point is needed. This includes the Gaussian filter coefficients, the low-pass filter used in decimation, and all intermediate results and final scores. A hardware-friendly approximation is needed also for the base 2 log computation. All these approaches will cause some precision loss, which means numerical issues would more likely to arise, and we need to handle them appropriately, such as clipping the variances to non-negative. Next slide, please. So in order to compare how our hardware-friendly implementation compares with the reference software, we built 2 simulation models, the floating point model and a fixed point model. The fixed point model contains all the hardware-friendly alternations we described, which include fixed point representation, approximation to the log functions, and various numerical stability guards. The floating point model is built by directly taking the floating point score computation functions from the reference software and put them in the same test harness as the fixed point model, so both models receive the same input images. We then feed 400 sequences of video and their transcoded versions to these 2 models. We then compare the difference between the scores reported by these 2 models. Next slide, please. So the table summarizes the average absolute difference between the scores reported by the 2 models for 4 metrics. We group the errors by video resolution and the QP value used in transcoding. It can be seen that the average error for the fixed point implementation ranges from 0.000004 for FFmpeg-based SSIM to less than 0.015 for VIF. The larger error for VIF is due to the complexity required in the score computation, such as the logarithmic function. These errors are deemed to be acceptable by our video software team since they are small enough and could be calibrated out by retraining the model using the overall VMAF score computation. Next slide, please. To conclude, hardware acceleration can tremendously improve the energy efficiency of video transcoding systems at scale. The proposed quality metrics architecture can greatly improve the performance per watt of objective quality metrics computation compared to CPUs. The proposed architecture can be further extended to use chroma channels and also to compute more complex metrics such as the full VMAF score. Also, leveraging encoding decisions not only reduces the overall compute complexities, thus power, required in the transcoding system. Due to the small data path width and less memory usage, this approach is especially beneficial for hardware implementation since it also reduces verification space and design complexity. This gives us motivation to explore more creative ideas in this space for future work, such as tuning the first pass statistics in video transcoding. This ends my presentation. Thank you for your attention. I will now turn it over to Yanni to start the panel discussion.
Thank you, Cindy. And again, I want to take a chance to thank the audience so far for their great attendance. My name is Yannis Katsavounidis. I've been at Facebook for a little bit over 2 years, and it's a great pleasure today to have with me at least Professor Al Bovic, our other guest, Professor Kuo, has some technical difficulties, and I'm not sure if he will manage to finally join us. But I think it's good to have you here, and I think there is nobody in this audience that doesn't know you. But having heard all these interesting presentations from Facebook, first of all, do you have any initial thoughts? You heard SSIM all over, mentioned by at least 3 of our presenters. What do you think so far?
Well, my first impression, of course, is that 20 years ago we had a vision that one day we'd be able to inject perceptual science, vision science, into video engineering applications. And so it's very gratifying to see this happen now at the greatest scales. Of course, we couldn't necessarily anticipate the degree to which video has begun to absolutely dominate our lives, especially during this COVID crisis. But it's an amazing thing overall. In terms of the presentations, I heard a number of topics that I thought were very interesting. One of which, of course, was something that we didn't really think much about for a long time, and even only recently it's something I'm hearing more and more about, and that's energy consumption of, well, let's just say of video in general. We've been talking about energy consumption by quality assessment models. Well, the internet today consumes almost 2% of all U.S. electrical consumption. Of course, a lot of that is data centers and so on, but it's also everything. All these devices and laptops and everything else. It's a lot, and it's growing. And when we realize that video is 80% of the traffic almost, or around, you hear various figures, we recognize that we in the video field we're responsible. 2% is a lot. And given increasing video demands, of course, it's only going to get worse. We're going to see, 8K. I'm convinced we'll see 16K at home in my lifetime, and bit depths and everything else. So investigating video quality assessment in terms of computation and energy consumption is important, not only for controlling people's quality of experience, optimizing bit rate, but also energy consumption. I think it's a new dimension that we have to add to these models, however it's expressed. In terms of VQA, I think it's wonderful to think that they're here to stay, but there's so much more work to be done. First of all, there's HDR. There are models out there for assessing HDR quality, but I think we have a long ways to go before we've really solved that. And even perhaps more so, higher frame rates. High frame rate videos are becoming very popular, sports and that sort of thing, and the devices can support it, but we don't really have perceptual models out there yet that fully exploit the temporal dimension to handle things like stutter and judder, all these kinds of things. 8K is coming, 16K is coming, and so on. So
I'm taking.
that's one of my first things. Yeah. Mm-hmm.
Yeah, and thank you for that. I think because of the audience, I believe there are a number of PhD students and researchers out there. What do you think is then the next frontier? You already mentioned higher frame rates, higher bit depths, right, and maybe HDR. But the much desired question these days is there room for neural networks and something that will go past the statistical or more classical approaches? And what's your take on this?
Absolutely. Deep video quality assessment models, this is one of our main research focuses right now in live. Of course, it's a data-driven subject, and so you need lots of data, which means we're doing really large-scale human studies, and these are ongoing right now, some of them, to collect literally millions of judgments of video quality. So I'm convinced that one day let's just call it neural video quality assessment will be the solution. But today, when you compare performance on data sets, simpler algorithms, when you see SIM being only 0.03 below a 10 million parameter deep model, it's hard to justify the expense of trying to build that in yet. But, so one day it'll come, but not yet, I think.
Good, thank you. And actually, this was my point. I mean, I sometimes see people forcing their way, right? They need to they feel compelled to include these models. And of course, the question that comes along with it, how much energy is this going to cost us? So always that energy trade-off is going to be important. But thank you. These are very insightful, comments coming from you, as you've said, for 20 years in this field. Allow me to go into a different topic, a topic that I want to hear also your thoughts. I actually just saw in the chat window a very interesting question that I was also planning to ask you. We hear about the adaptive bitrate streaming, which is a de facto standard of delivery today, where people are using this classic approach. You take a content, you encode it n times. Each of them are encoded more or less independently, right? And then they are streamed based on a client decision to switch up or switch down. That's a very simplified way of doing so. Of course, in the past, the concept of scalable video coding has been visited and revisited. And unfortunately, even though a good standard came out of it, it was never adopted. Instead of going into why it was not adopted, which of course I would like to hear your thoughts if you have some, I would like to ask, is it time for us to revisit that idea and maybe put some new thought in making a system that's going to be more scalable, naturally scalable? And what are your thoughts on this? And perhaps how does that fit with not just video coding, which must include this scalability aspect, or could include, but also the quality metrics themselves?
Sure. Well, why, SVC didn't really make it big? Well, I mean, there were a lot of good ideas in there. Like JPEG 2000, there were reasons, why it didn't make, which were a nexus of, well, harder to implement, not guaranteed to work the way you wanted it to in every instance, and maybe just not being worth the extra expense to try to create that when there's other ways of doing adaptive bitrate. That said, I think that scalability in every way is highly desirable. More granular scalability, for example, than adaptive bitrate schemes give today. I mean, this really goes to the question of the hybrid codec overall, actually. I think the hybrid codec is one of the greatest engineering achievements of all time. If you think about it, the impact that it's had. But it's being pressed to the limits of its ability to exploit redundancy. I mean, bigger screens help and that sort of thing. But, my advisor, Tom Wong, who, by the way, was one of the founders of the hybrid codec, he said in a different context, he said most of the advances of computer vision are advances of the computer. Well, I think a lot can be said about video compression. And the reason why I'm bringing that up in this context is that I think the end of the hybrid codec isn't that far off. And along with that, motion estimation, motion search, motion compensation. This is a great big energy hog. My background is in visual neuroscience as well as video engineering. And the brain does, while it does compute motion fields for other reasons and so on, it's not involved in the efficient representations of what we see. It's not part of compression, in other words. And I don't think we need to do that. So, going back to neural methods, we see, special sessions, a lot of activity in deep compression models. I think that, we're a generation away from deep compression, but I think it's going to happen. Going back to scalability where this started, I think this is where we will finally see granular scalability happen when we have deep architectures for conducting video compression. I don't think these architectures will require motion search. Instead, they will rely on highly parallel space-time interpolative processes, of which motion estimation is a too complex version. Deep learning networks are really good at interpolative type concepts. You can see these GANs and so on. And so I think we'll see motion-free compression as an outcome too.
Very good. Thank you. I really appreciate it. And I just saw Professor Koo just joined us. And it's so unfortunate that Dr. Koo, I would at least like you to give a welcome to the people. I know you've had technical difficulties, but unfortunately you joined us towards the end of the discussion. And thanks to Professor Bovik, who answered some of the questions we had. I want to take the time to thank you, both of you, for joining. Again, it's a great pleasure for me personally and for Facebook to collaborate with you in these great problems. We look forward to extending our collaboration in the fields of both video quality and video compression. And again, with that said, thank you one more time, and it's time to pass it back to Sankar for his comments. Thank you.
Thank you.
Thank you. Thank you. Yeah. Okay. Thank you, Facebook team. I think this was a great, thought-provoking session, and I think we'll have also a post workshop session with some questions. I'm not sure if someone from Facebook team would like to share the message room for that in the chat. The link to that. That would be great for all.
Thank you.
This was a great turnout from the attendees also, and I would like to congratulate Facebook team for this great turnout, and look forward for new sessions in the future. Also, I would like to let know the attendees that we are, just after this session, we are going to have Tinset workshop also. So everybody is up to it.
Thank you, Hassan. Thank you, Anil, and
see you in the next session.
Thank you, Dr. Bovik, Dr. Kuo, and all the great speakers we had. Thanks to Alyssa, who did all the logistics behind the scenes. And again, thanks to everybody who had made time for this talk. Thank you so much.